sulfuric acid. And it makes sodium sulfate and water. Two of these. And that'd be 4, so we need 2 here. I think that's balanced. Is that right? That is not neat, though. So it's 2 NaOH plus H2SO4 makes Na2SO4 plus 2 H2O. All right, so let's say we have 3 molar sulfuric acid. And we have 10 milliliters. And we want to know, and it took 50 milliliters of sodium hydroxide to titrate it. And we want to know 2 things: the molarity of sodium hydroxide and the mass of sodium hydroxide required to titrate it. Not mass of solution, but mass of the actual chemical. Yeah, I do just about have a zoom. Okay. So we've got 3 numbers, right? We've got the 50, the 3, and the 10. The 3 and 10 have to do with sulfuric acid, and the 50 has to do with sodium hydroxide. The first thing I usually have to do in these, ignoring the part where you have to convert from milliliters to liters, the first thing I really want to calculate is moles of something. Which one do I have enough information about to get moles? Sulfuric acid or sodium hydroxide? Sulfuric acid, right. So the one that you're going to start with is the one that you have both pieces of information for. You have to have enough information to get moles. The one you don't have enough information to get moles, you're actually, yeah, that's right. You're just going to kind of, you'll use as you, let me show you how to do it. My breath is not working. That's such a common thing for me, unfortunately. All right, so we're going to start with 10 milliliters. Anybody know how much 10 milliliters is in liters? Yeah, 0.01, because you're going to move the decimal place. All right, 3 places. So 0.010 milliliters of H2SO4. And we're going to use the molarity. Oh, thank you guys. Just making the amount smaller and smaller. All right, so I'm going to use molarity. And the molarity is 3 molar. So how many liters is it? So we have liters on the bottom and moles on the top. So how many liters on the bottom? 1. And how many moles? 3. Good. Because molarity is moles per liter. When it's per liters per 1 liter. And this is H2SO4. All right. Once we're at moles of H2SO4, where do we need to go then? Because we start out here, and we want information about that guy. Yeah. So we're going to go to the thing we need information about. So we need information about sodium hydroxide, so we're going to go moles to moles there. So sulfuric acid goes on the bottom. Sodium hydroxide goes on the top. What number goes with sulfuric acid? Good. What about sodium hydroxide? Good. Good. And I'm getting those numbers from here. Wait a minute. Try that again. Here, that number went here, right? And then the 1 went there. All right. So at this point, I have moles of sodium hydroxide. So how many moles of sodium hydroxide do I have at this point? It's going to be 0.01 times 6, so I guess that'd be 0.06. All right, so it's asking me two things. One is molarity, and the other is mass. Which one do you guys want to calculate first? Because we can calculate both at this point. Let's do molarity, all right? All right, so moles of solute. So the thing dissolved is sodium hydroxide. So that's going to be 0.06 moles divided by liters of solution. How many liters of solution do we have? Yeah, good. And the solution that it's referring to when you do molarity is the solution of stuff that's dissolved. So we don't want the total solution of sulfuric acid and sodium hydroxide. We just want the solution, the sodium hydroxide solution, because that's all we're interested in. Okay, and that's coming from this information that they gave us. So we just converted that to liters. So what's the molarity of sodium hydroxide in this case? 1.3. Or is that 1.2? 1.2, okay? All right. Now, how do we get grams from all of this information? Moles to grams, correct. Molar mass, awesome. You better remember the molar mass of sodium hydroxide. I think it's 40. Let's calculate it. Yep, 40. Oop, and I put it in the wrong place. So how many grams of sodium hydroxide do we have? .4. All right, and that's 2.4 grams of sodium hydroxide in 50 milliliters, not necessarily in the whole batch, but in 50 milliliters. That's the amount that it took to titrate it. Now you could go another direction with this also. You could say 2.4 grams of sodium hydroxide was used to titrate 10 milliliters of sulfuric acid. If 50 milliliters of sodium hydroxide was used, what's the molarity of sodium hydroxide and what's the molarity of sulfuric acid? So if we were doing that, do it right here, we would go grams of sodium hydroxide to moles of sodium hydroxide, and then moles of sodium hydroxide over liters of sodium hydroxide. And then we could say, well, we had 50 milliliters, so that would be volume of sodium hydroxide to moles. Actually, we wouldn't even have to do that. Once we had moles of sodium hydroxide at the top, we could just go straight to moles of sulfuric acid using the coefficients. And then divide by the 10 milliliters. You get the molarity for that too. All right, any questions on titrations before we move on? Nope. Awesome. You guys are great. All right. So what we're looking at today is solubility rules. So I'm going to pull that up today. How'd you like my questions today on the quiz? They were kind of long. I decided to tell little stories with them today. What am I looking for? Lengthy. Yeah, they were kind of long. Let's see here. Okay. So these notes that I'm going to go over right now, and I owe you guys some slides. I've just got to remember to do that. Yesterday, I literally spent the entire day doing emails. I was trying to get to grading. I had so many emails. It was emails literally all day long into the evening. So I'm hoping tomorrow and Friday, I can get some grading done. I don't know. Got to get it done, though, and the semester's coming. All right. So let's say, okay, so we have a precipitation reaction. And RXN is just my abbreviation for reaction. All right, so what's the purpose of a precipitation reaction problem? And learning the solubility rules and all that. What is my purpose? What could I use this for if I was working in a lab? And I wanted to save money on chemicals. I could use it to predict the outcome of an experiment before I do the experiment. Right, so let's say I needed to mix silver nitrate and lead chloride. No, not lead chloride. Let me do a different chloride. All right, let's do sodium chloride solution instead. All right, and both of these are aqueous. And let's say in my lab, I need to mix two things together to get a solid. I don't know why I need to do this, but for some reason, I need to get a solid. And I have these chemicals in the lab, so I want to see what's going to happen. I could look at my solubility rules and figure this out. So when these things go into solution, you get this. All right, and there are a bunch of different ways they can bump into each other and react, right? So the sodium can bump into this chlorine and produce sodium chloride, which would just then dissolve, right? The silver could contact this nitrate and just dissolve. So that neither of those would do anything. Actually, no. The reason is because nitrate is minus and silver is a plus. So they're not held together as tightly as, let's say, something that had like a +2 and +3 charge, or -2 or -3 charge. Those things just have more of a pull, And these things are just easier to dissolve. The water can actually pull them apart because they're not held quite so tightly. So if they bumped into each other like we had them up here, nothing's going to happen, right? They're just going to be ions still. But the other option is the silver could bump into the chlorine. And the sodium could bump into the nitrate. And then we have to decide if a reaction occurs. A reaction only occurs if something on the right is a solid, a liquid, or a gas. If it's solid, liquid, or gas, it doesn't have to be both things, just one thing. Then a reaction occurs. The reason I say a reaction occurs is because two things will stick together and stay that way. So that's when the solubility rules come in. So if we look up the solubility rules, one thing we notice is that anything with a group 1 metal is always soluble, and anything with a nitrate is always soluble. So that's going to be soluble. If it's soluble, I write AQ. And then when we look up silver chloride, we find that that solution is insoluble, meaning it doesn't dissolve. It forms a precipitate, which would be a solid that forms. And so we would write an S there. So in this case, a reaction does occur. And you can also tell this once you've written out the net ionic equation. Right, because this sodium nitrate would break apart into sodium and nitrate and leave us just silver and chloride. Right, so there's something left. Yes, you definitely need to memorize the solubility rules. There is a chart in the textbook that I actually like. I'll tell you about the chart in a few minutes, but to me, there's a pattern to the chart, so I like that. All right, so I know something happened because I have a reaction left here. Yeah, I know. Once you've worked a bunch of problems, so you start to get used to the exceptions. Just takes a little bit of practice. Yeah, I think you're right. Okay. So let's see. All right. So let's say we had this instead. Well, now that would just give you all the same stuff. Let me think of some other way to put it. Well, I'll just go over some stuff, and I'll show you what I'm talking about when we get to it in a few minutes. All right, if you look in my notes, I have one where we've got a sodium carbonate example where it's just showing something dissolving, really. And then we've got magnesium carbonate dissolving as an example. And then we've got potassium iodide and lead nitrate and what happens there, which is basically like, it's just like the one that I showed you in that a solid is formed. All right, so here's a good one. So this is one where no solid is going to be formed. All right, so if you look up KCl and NaI, you'll find that those are both soluble. They both contain things that are in group 1. Everything in group 1 is always soluble. So if this is the case, then I split everything up into its ions. All right, and then all of these would get aqueous symbols, but I'm going to be a little lazy and not put them in. So let's get rid of some of the spectator ions. Right? So if I get rid of sodium, get rid of chlorine, get rid of iodine, get rid of potassium, then what I'm left as a net ionic equation is an arrow. Right? That's not an equation. So what they say happens at this point is they just write no reaction, because there were no solids, no liquids, and no gases formed. So those are the two options you can have. You can either have a reaction or no reaction. So let me see. All right. Yes, you do have to balance it to start with. In this case, they were just, coincidentally, they were already balanced. Arif, what's your question?
Is it possible practically?
Is what possible?
I mean, you break the equation like K positive, iodine negative. Can you do it like practically that there will be no reaction if we perform this experiment?
Yes, and the reason there's not going to be a reaction is because, to begin with, since the things on the left are already aqueous, you have all of these ions floating around in solution. And then when you finish, since these things are soluble, you still have only these things floating around in solution. So in the solution, nothing's really changed. It's just a bunch of ions floating around. That is a good question. All right. Okay. Now let's take a look at the solubility rules. All right. So I'm going to start with the ones that are soluble. What is a color that makes you think soluble? Red, orange, blue, purple. Blue, green. How many people say blue? How many people say green? All right, so we'll go with blue right now. But I can see why you'd say green too, because green is like go. So it's like a yes. All right, so we've got lithium, sodium, potassium, and ammonium. One thing to note about these is most of these are in group 1. Things in group 1 on the periodic table, the alkali metals, are soluble when you mix them with anything. And ammonium also. There are no exceptions to these 4 things being soluble. Right? And here are some more that have no exceptions. So these are all positive things. These are not negative things. Nitrate and acetate. No exceptions there. They will always dissolve no matter what you mix them with. most of the time, and I'll do purple for these. Well, I'll do blue for this part. Okay, most of the time, chloride, bromine, or bromide, and iodide will dissolve. There are a few exceptions. The exceptions are when you pair it with any of these. If you pair it with silver, mercury, lead, then it would be insoluble. Yeah, the heavier metals. Most of the time when you see lead, it's not soluble. Most of the time when you see mercury, it's not soluble. Silver can be soluble, but it's not when you mix it with a halogen. Remember, halogens are just the name of the things that are in group 7 on the periodic table. So it's fluorine, chlorine, bromine, iodine. Correct. If it's not soluble or insoluble, then it will form a solid. Or it will stay a solid. It won't dissolve. So then we have SO42 minus. That is normally soluble, but it's not soluble when paired with silver, lead, calcium, strontium, and barium. Think of a barium swallow. If you go to the doctor and you have a test done to see if you have reflux or something like that, and they want to x-ray your esophagus, they will give you a barium swallow. A barium swallow is where they give you this chalk-like stuff. My kids had to go do it one time, and what they do, it's awful. They take this chalky liquid and they put Kool-Aid in it, and they tell them to drink it, which my kids all said Kool-Aid did not make it better. It was disgusting. But the barium was insoluble. That's why it was so chalk-like. But it being insoluble made it where it would show up on the x-ray. So that's why they picked that. All right, so this is all the soluble things with their exceptions. Notice that exceptions in both cases are silver and lead. In most of the cases, the things that are insoluble are positively charged with a 2+ charge, right? Not always, but in some cases. Anybody need a second on this page before I go to the insoluble things? Yeah, okay. Just let me know when you get finished. I didn't know that gold was soluble in mercury. That's interesting. That's very interesting, actually. All right, so let's do insoluble in red, because to me, red is like a no color. So insoluble. And these are the exceptions. So the exceptions mean that it will be soluble. That's why I used blue. All right, insoluble things usually are mixed with hydroxide or sulfur, unless they are paired with one of the things that is always soluble. For example, things in group 1. You know what? Oh, shoes and socks. I have to rewrite that whole thing. Sorry. Okay. Yeah, shoes and socks. That's something I learned to say around my kids. That is not a bad word. So now that I'm older and I don't like to use bad words, I will say things like shoes and socks. So my daughter actually has gotten into that habit. She learned that from me. She teaches at a preschool. I'm sure some of the kids, she teaches 2-year-olds and they pick up a lot of things. I'm sure that some of the things that they go home and say are things like shoes and socks, which the parents, I imagine, as soon as they start, they're like, no, but then it comes out shoes. So it's not so bad. Amelia, what's your question?
I am very confused on the chart. I thought we were supposed to be doing the insolubles. And how is lithium soluble except with lithium?
Well, you know what? When I rewrote the chart, I wrote it in such a hurry that I wrote it wrong. That is a very good question. We are doing the insolubles.
Okay,
I'm
thank
so
you.
glad you pointed that out. You're welcome. Yeah, that wouldn't make any sense. Lithium's soluble unless it's with itself. In which case, no, that would be crazy. That's what I was writing. The soluble chart was the first one. So everything I wrote in blue, soluble. Okay. All right. So all the exceptions in this case are soluble because everything on the left is usually insoluble. So if you see a hydroxide or a sulfide, usually it's going to be solid unless it's mixed with one of these things. And if you notice, everything in this list is one of the things that was listed in the soluble list as having no exceptions. So it makes sense that the insoluble things are always insoluble unless they're mixed with something that has no exceptions. All right. And then, let's see. There are a couple other things. If you take these things are for everything, hydroxide and sulfide. The things I'm going to write now are just when you mix sulfide with them. Okay. Time's up. Oh, crud. Okay. All right. I've got one more. I'm going to write it really, really fast. Okay. All right. So that's it. That's all I've got. All right. You have a nice day too. Okay, so the middle, this and this, both of them work for that. With the middle one, it's only the sulfur that works with those as insoluble. So if you paired hydroxide with calcium, that should be insoluble. However, if you paired calcium with sulfur, that would be soluble, if that makes sense. All right, these are the rules that you use when you want to make sure, when you want to see whether or not something reacts. All right, what's your question?
Professor, whenever you make the mistake, you can always press Control Z to go back instead of writing it all over again.
Oh my gosh, goodness gracious, I forgot about that. Thank you, Arib.
You're welcome.
That would save me so much time. So when the extra credit will be graded, I'm hoping to get it done tomorrow. I've got to get some extra credit. You guys are slightly, believe it or not, slightly ahead of my other chemistry class in grades. But I'm hoping to get a lot of stuff done tomorrow, which means I probably won't be answering emails tonight or tomorrow because I'm going to try to grade instead. And then I'll probably try to answer some emails on Friday and grade on Friday. So the adaptive thing works like this. Are you talking about the adaptives that I just opened up, like the old ones, or are you talking about adaptives in general? Okay, so the old adaptives that I've opened up, if you turn it in late, which would be any time between the due date and Friday, you know. So if you do it this week, you can get half credit. I'll have to go in and manually change the grades to half credit. So like if you got an 80, that would be a 40, and so forth. Oh yeah, on the extra credit, that is effort. Like if you try, you get full credit. So even if you can't figure it out, but you gave it a shot, I'll give you full credit for that. So that is not a problem. Yes, we can. We'll do some more solubility questions. Just have the solubility rules handy. Oh yeah, that's a good point. So if you try the adaptive, you get 100 if you put in a good effort, regardless of what the adaptive gave you. So the lowest grade you could get on an adaptive would be a 50, and that would be if you turned it in late and ended up with half credit. Otherwise, if you tried, you'll get 100, which means there would never be a grade of an 80 on an adaptive unless somebody only tried for like, I don't know, 30 minutes or something. They didn't give it a really good try or something like that, you know. Roger, what's your question?
I'm like saying, like, let's say I have an adaptive from like 2B or something, and I had an 80 on that, and then I attempted it and got 100. What would that score be? That's what I'm saying.
That would still be an 80.
Okay.
Yeah. Do keep an eye on it. If you try again and somehow I put in a lower grade, but you got a higher grade before, point that out to me.
Okay.
Yeah, your homework is still due on the 29th. Oh, wait a minute. Yes, no, that's right. Does last work say it's still due on the 23rd? Does it just say that on D2L or does it say it on Smart Work also? Does say the 23rd. All right. Well, I'll have to fix that because all the